Would you mind reading the problem?
A string can withstand a maximum tension of T without breaking. A student ties a stone with mass M to the end of the string, and holding the other end, whirls the stone in a vertical circle of radius r, increasing the speed of the stone until the string breaks. The center of the circle is at height h above the ground.
I'm writing down all my givens. H. What else? Maybe read it again.
Oh. A string can withstand a maximum tension of T without breaking. A student ties a stone with mass M to the end of the string and, holding the other end, whirls the stone in a vertical circle of radius r, increasing the speed of the stone until the string breaks.
What a cool problem. So, did you figure out? Did we figure out where that was most likely to break?
Yeah, the bottom.
And h is the height from the center of the circle to the ground. Is that right? Let me just check that. I think that's true. So that's h. All right. And then let's. This is rock at top. This is rock at bottom. And so we figured out already probably that the tension is greatest at the bottom. So I'll do that real quick. So at the top you have a force diagram where tension, there's the rope. So tension would be down, right? Because there's a rope pulling down on the rock, and there's also the earth pulling down on the rock. So that's weight, and then that's tension. And then your net force has to be down. When you add those vectors, weight and tension are in the same direction. So we have mv squared over r, because we're assuming the rock goes in a circle with a constant speed. So we have mv squared over r. Wait, I messed that up. I totally messed that up. We have mg is the weight and tension. And those two vectors, those add up to our net force down, which has a magnitude of mv squared over r. So at the top of the loop, our tension force, tension in the rope, is mv squared over r minus mg, right? That's at the top. Now let's do the bottom. So at the bottom, we have, let's see, our force diagram changes. The rope is pulling up. The earth is pulling down, right? And when we add those vectors, actually, I think the tension has to be much greater than the weight. So I'm going to draw the weight like short. The weight didn't change between these. The rock didn't change weight, but I'm just drawing it shorter. So tension is going to be longer than the weight down. Weight down is mg, tension is t, and our net force now is up. So now our mv squared over r is upwards. So you can see from that vector sum diagram that tension is equal to mg plus mv squared over r. Cool. So what we found is that at the bottom of the loop, more tension in the string. And that means it's more likely to break at the bottom, right? So, more likely to break while rock is at the bottom of the loop. Okay, so now that we've done that, we can actually find the tension. I think we're given, we need an expression for the speed of the stone at the bottom. Is that right?
Yeah.
So I can just rearrange this. I'll do it like right here maybe. So mv squared over r has to equal tension minus mg, right? And then mv squared over r, let's see, mv squared has to equal, I don't know, r times t minus v mg, right? And v squared is going to be r over m. Hi. Okay, take care. He finished a quiz. Be patient, I'll figure it out in a little bit. So v is the square root r over m t minus mg. There it is. Actually, just, I'm sorry, I couldn't log in right here, so I can't do it.
Tomorrow during lunch?
Sure, that works. I think that's done, right? So let's plug in the numbers and maybe calculate what v is. So what's r, please?
R is 1 meter.
Say that again, I'm sorry.
1 meter.
Oh, 1 meter, okay. And then what's m?
M is 0.8 kilograms.
Okay. Alright, and what's t?
100 newtons.
100 newtons. Minus what's m again?
0.8.
0.8 kilograms.
Yeah.
And then what's g is 10 newtons per kilogram. And all that's inside a square root. So this is going to be 1 over 0.8 times 100 minus 8. Is that right? And kilograms cancel. So, and we have all of this inside a square root. So we have square root of 1 over 0.8 times, what, 92? You guys have a calculator handy? Thank you. Hopefully this works out. Yeah. It's the same thing as square root of 92 over 0.8, right? I think we could use Desmo. Alright, so we get, what, 10.7 meters per second. So we get that speed, right? Now, so the rock breaks, the string breaks, and that's how fast the rock is moving horizontally. So now it's basically a projectile problem. So we'll remember the new page. So this is the projectile part of the problem. So it's like it's a projectile moving 10.7 meters per second. So that's our v in the x direction, right? And the projectile is gonna like do this, yeah, and then hit the ground. And in the vertical direction, we could say that delta y is 1/2 ayt squared, because we have no initial velocity, right? You know where this comes from? And this is the area of our velocity graph, right? It's the area of that triangle, basically. And so if I solve that for t, I get square root of 2 delta y over a, right? And I think we know that the height of the height h was double this height. This is h over 2, right? So we know delta y is h over 2. Are we given real numbers for this or no? Oh yeah, we are. So h equals 1.5. So this, what's half of 1.5? 0.75? 1.5? Yeah. 0.75? So we know h over 2. We know the height's 0.75 meters, right? So square root of 2 times 0.75 meters divided by 9.8 meters per second squared. Let's see what that time is for this projectile to hit the ground. Okay, so we got t equals 0.39 seconds, and that's the time to hit the ground, right? Now we want to know the range, which is how far horizontally. That's our delta x. Delta x is the range of a projectile. So in the horizontal direction, which I'll do in green, we know that the velocity is constant. So the area of a velocity graph is velocity times time, right? So delta x is going to be v in the x direction times t, right? And if I solve that for delta x, I get, what was our velocity? 10.7 meters per second. And the time to hit the ground, 0.39 seconds. So what do we get here, please? No, it's okay. You're the coolest. It's all good. 10.7 times 2.39. So we got 4 I'm gonna say 2 meters, right?
Yeah.
That would be the range of the projectile. So if we want to know where the stone will hit the ground, well, it hits the ground 4.2 meters away horizontally from like if you mark a position on the ground below where the rock was launched. So it's going to travel 4.2 meters horizontally. Yeah, hope that helps. It's cool how that problem incorporates almost everything we've done. Pretty neat. Anyway, hope that helps.